I want to show you how to measure voltages and currents in a circuit. I'm not going to worry about the specific resistances in this case because we know how to measure resistance. Now let me say, if I want to measure R3, I can't have it in the circuit. I have to break this and then measure across that. Okay, if I measured it in the circuit, I'd be getting the resistance of, if I put two probes here, I'd be getting the resistance of the entire circuit, which is a little weird because resistance is a passive thing and voltage is active, or excuse me, a battery is active. So I wouldn't get a reliable thing. Even if I took the battery out, if I went between here and here, I would be getting the parallel resistance of R2 and R3. So basically, disconnect the battery when you're trying to measure individual resistances. Disconnect the parts that you don't care about. If I did want to find out what the equivalent resistance of this was, what I would do is I would take my multimeter, I would set it to ohms, and I would connect it from there to there. And that would give me the equivalent resistance, okay? But we've talked about resistance. What I want to talk today about is how to measure voltage and current in a circuit, okay? And what I've got is a 9-volt battery. I'm going to write it as, in quotes. It doesn't provide actually 9 volts of potential difference between those things. And we know that this is the positive side based on that symbol. So I actually made this circuit, and I'm going to show you how to measure things on this circuit. First thing you got to know is a voltmeter. Voltmeter, the symbol is like this, and the voltmeter is, you can think of it as infinite resistance. In fact, let me just, resistance. Well, think of air is going between, there's air between here and here, right? So the air is infinite resistance. So you can think of attaching a voltmeter doesn't change the current in any way, okay? So what I can do, unless I break the circuit, unless I open up the circuit and insert the voltmeter into the circuit, but voltage, remember, is a potential difference. So what I can do is I can go and I can evaluate voltages without changing the circuit. This is no different than having air between here and here. In other words, having having this whole thing in an environment of air. Sorry about that. That's a little confusing. So if I want to measure the voltage across R2, I could do this or this, as long as I'm aware of what my specific polarity is, what I'm considering to be the base polarity, the common, the reference polarity. So let's go through this circuit, and I'm going to do it and do a picture-in-picture. You can see what I'm measuring. So I made this circuit, and I even labeled R1, R2, R3. It's a little hard to see the circuit itself because the white breadboard ends up being very oversaturated. So if I want to find out the voltage, actual voltage across this, I take this and I attach it like that. And when I did that in the actual circuit, I got 9.37 volts. 9.37 volts. So actually this is providing a potential difference of 9.37 volts, with that higher than that. Okay? By the way, if I disconnect, when you actually connect the battery up, it doesn't provide the same voltage as the voltage on the battery when it's out of the circuit. That's because there's internal resistance to the battery. So if I break this, so current's not flowing through the battery, and I measure this, what I end up getting is something different, 9.33 volts. That's really weird. It shouldn't happen that way. It should be actually less when it's in the circuit. I may have had those backwards. Okay, so let's just say 9.37 volts is what's provided by this, the difference in potential energy. Now I'm going to go and I'm going to measure R1. Now, look where my black and my red are. I don't really care, honestly. When I measure it this way, I will find a positive 4.92 volts, where this side is more positive, higher potential energy than that side, 4.92 volts. Okay. If I measure the other way, if I do it this way, I'll find that I got negative 4.92. In other words, compared to this, this is lower. So what you want to be able to do is label the resistors and show what the voltage difference is across those resistors. Okay, if I do this one, again, I'll put the black on the bottom. If I do R2, what I find the voltage difference is 4.4 volts. And this was the higher side. And if I do it across R3, guess what? I also get 4.4 volts. That makes sense because these wires are connected together up there, and these wires are connected together down there. So whatever voltage difference there is, let me draw it with different color, between this wire and that wire has to be the same as the voltage difference between this wire and that wire. That's all just one big piece of metal. So those voltages are the same. Well, let's check out. If I go around the loop, Kirchhoff's voltage law, plus 9.37 minus 4.92 minus 4.4, and what I ended up with is 0.05. Okay, so there's something in the measurements that's a little off. Could be resistance in the wire. I don't think that's a big deal, but I started here, went up 9.37, down 4.92, down 4.4. Kirchhoff's voltage law tells me it should end up being 0. Okay, and if I did the same around this loop, I'd get that same result. Okay, so these two add up to be the same as 9.37. If I climb up the stairs or I go up a ramp to get to that same spot, I should have gained the same amount of potential energy. So that's how you measure it using a voltmeter. Now, current using an ammeter is a different beast, and it's a little more dangerous. Not for you, but for your circuit and, for your multimeter. This is 0 resistance. It behaves like a wire. Remember, current is through something. So think of it. Let me get rid of my voltages. We've figured out all the voltages. And by the way, if I do the voltage across any wire, like from here to here, I should get 0. Voltage across from one point of a wire to another point of a wire. Current through. Okay, so if I want to find the current through the battery, I can't just switch it over to current and go like that or that. Oh no, because this is a wire. If you connect a wire across the battery, it's a short circuit. It means current will go through the wire instead of going through the circuit. So whenever you insert an ammeter, you have to break the circuit and make the current go through this. Pretend it's a wire in the diagram. So, let me, before I move on from the voltmeter, if I wanted to draw how a voltmeter would be connected here, I would do it this way. Okay, that's how I did it. I touched across that. Infinite resistance, no current goes through there, everything behaves the way it did before. So that's how you would do it with a voltmeter. With an ammeter or current setting of a multimeter, and by the way, this is called ammeter, not amp meter, ammeter, when it's on the current setting. I have to break the circuit and then insert this as a wire in the circuit. So when you do that and you spell ammeter correctly, what you do first, break the circuit, and then 2, reconnect using the ammeter as a wire. That will mean that the current goes through the ammeter and the ammeter can measure. Remember, current goes through things, so you have to make the current go through this. So if we look at this, if I want to find the battery, the current coming out of the battery, what I need to do is break it and then hook up on the current setting, hook it up like this. It's assumed that a positive current means it goes in the red and it comes out the black. So if I hook it up like this, I get a certain measurement, and I think the current I end up getting is 4.9 milliamps. So it went in through the ammeter to there, came out. So current went through into the ammeter and out the other end of the ammeter. So that's the way you draw it. Break the circuit. If you don't break the circuit, you've got a really good chance you're going to blow a fuse on this sucker. Okay, so that's how I measured that one. If I measure R1, guess what? I can do the same thing. Because whatever current went through here had to go through R1. And I think I demonstrated that by putting the ammeter in here, but you don't have to, because I already took a measurement. In fact, anything that goes through here has to go through here, has to go through there, has to go through there. So anything in this branch of the circuit is going to have the same current. Okay, the voltages will be all different, but same current. Now, if I want to do R2 or R3, let's do R2. I disconnect. I'm going to pull a leg of that resistor out, and then I'm going to reconnect using the ammeter. And once again, if the current's flowing this way, I'll get a positive number this way. Let's think of it this way. We know the current here, right? That's about 4.9 milliamps. If I had broken this, inserted the ammeter like this, and had this as the red side, I would have gotten 4.9. If I had it like this, I would get negative 4.9, because it's assumed that it's coming in the red and going out the black. Okay, so be really, really careful with your measurements there. Okay, so when I do my ammeter in here, what I ended up with is 2.9 milliamps. So the current through here is 2.9 milliamps. Now, if I want to measure this one, I break it, reconnect it using the ammeter, and what I measure is, in this entire branch over here, the current is 2.0 milliamps. And look, this makes sense. 4.9 milliamps come this way. It's got to go somewhere. 2 milliamps go this way, 2.9 milliamps go that way. In fact, from this, I can conclude that this resistance must be bigger than that resistance. It's easier for charge to move this way than it is to move this way over the same voltage difference. So that's how we measure currents and voltages in a circuit.